Hello, statistics student. This video is for chapter 10.1 and 10.4. We're doing hypothesis tests for comparing two population means. To do the hypothesis test, of course, we would need to collect two samples, one from each populations. Just like in proportion, we would compare them using a hypothesis test procedures. The difference with this compared to proportion is there are two kind of samples when we are comparing means. One is called independent samples and the other is called dependent samples. Now, this has nothing to do with of what we have done in chapter 3 about two data are dependent or samples are independent because they're lower than 5%. Nothing to do. It's just the name of the types of the samples. So because I think statistics like to use the same term again and again. So in this particular case, when we are describing the samples from two populations, if they are dependent samples, the sample values from one population are not related to or naturally pair or match with the sample data from the other. So you can just collect a sample from one group of population, like male, you collect 20 males data. Female, you collect 20 females data. So the sample size can be different or they can be the same. And usually we will have summary statistics. Sometimes we do have data, but a lot of time we just have sample statistics. But what is dependent data then? Dependent data would be we still collect two samples from each population, but each values are paired up. You can actually tell, okay, this value is paired to the other one. So the most common one are you collect, like say for example, you want to collect something from male and female, but the male data and female data are couples, they're husband and wife, or the male data and the female data are brothers and sister or twins of a sibling. So there is some kind of matching up between the two samples, although it's still male and female. So this match pair does not means cause and effect. Doesn't mean that the second one has to be dependent on the first one. It's just describing that they are pairing. Okay, and because of pairing, so the sample size must be the same. We do not use N1, N2. We just say N. And usually you would not have summary statistic. They give you the pair samples. So what happens is if you're comparing two mean or two population measurement, if they are paired up, so what you can do is you do not compare the two samples at all. You actually compare each individual differences to see if there is actually changes. So pair samples allow you to do pair differences, but if they are not pair sample, they're independent sample, you just compare the sample mean. So let's do some practices to identify if you have a pair and or independent sample. So first is height of 14 men, height of 16 women. A very clear indication that this is independent would be they have different sample size. They can be matched, right? So that you can say that the samples are paired. You are comparing sample mean only. You're comparing x1 bar versus x2 bar because the data values are paired, not paired. This one would be what I've just talked about. So we still have heights of men and women, but the height is the husband of a couple and there's a typo here. And the sample 2 is the wives of each of the couples. So each pair values are from the same couple, so these samples are dependent, so they pair up. And when we compare them, we don't compare the sample mean of the whole first sample. We actually calculate a difference from each pair, which is x1 data minus x2. So we say, okay, for each couple, what is the difference? And that would translate to understanding if if the sample mean for the two population actually the same or difference. So let's see. This is the steps. Okay, so this is what I think this is the talk about the theory on how to compare independent samples, and then the next part is how can they use paired difference, a new variable that we create called D to compare population means. So how do I compare population means if they're independent samples? So I just talked about that. We're just comparing x1 bar and x2 bar. And whenever we're comparing something, which is just a sample statistics, we would look at how they distribute, right? If x1 bar and x2 bars are normally distributed, which is possible because of central limit theorem. So if they are normally distributed, then the difference of two normally distributed data would also be normally distributed. But what is the standard deviation? Because if something is normally distributed, we want to find out the tick mark, right? So this standard deviation of x1 bar minus x2 bar would has a value, which is the sum of the variances. So the common case is we pretend sigma 1, or actually we most of the time, we don't know sigma 1 and sigma 2. So it turns out that we cannot add the sum of the variances. We have to use the sample variance to approximate them. And once you use sample variance, the distribution would not be modeled by Z. It would be modeled by T distribution. So again, both sigma 1 and sigma 2 are not known or given, which is most of the common case. You would use T distribution where this is the sampling error. So it's supposed to be, so this is the sampling error of x1 bar minus x2 bar. Okay, so you would know that, okay, I can draw the pictures of x1 bar minus x2 bar, right? So whenever I collect two samples, I subtract the bars. But how many tick mark is my sample away from the x0 value, which is, we always assume that they are 0. We are always in x0, we always assume that it is no difference. They're exactly the same, and then we find out where our sample is. And this is the size of one standard deviation, one tick mark. It's very big. Okay, so it's basically sum of the sample variances. Remember, it was s1 over square root n, right? Or s over square root n. If you square it, become a variances. You add the variances and do a standard deviation. That would be how big one of this tick mark is. Now the degree of freedom of the t distribution will be more complex. It will be something like that. I don't even want to talk about it. So this is not possible if you're doing it by hand. You have to use statistics to do. So again, I'm going to put it here in the notes. By default, when sigma 1 and sigma 2 are not given, we assume that they are unknown and also unequal. Now this is, if you want to test that they're equal, you can do a hypothesis test of sigma, which is not covered in this course. But statistics has the command available where you can compare them. So if they're not equal and unknown, we would we would not pull the variances. So that means we do not add the samples together like what we did for proportion. We just add the variances together. This is called not pulling the variance. So that is when we have dependent sample. When we have an independent sample, and we have this is an independent sample. When we have a dependent sample of paired data, what do? Like what we say, we look at how each one is different because they are pair up. So we just compare, or we actually calculate the difference of each pair, D equal to x1 minus x2. So we forget about h1, the first sample, and we forget the second sample. We actually create a new data variable called D, difference of the paired. So if x1 and x2 are normal, the bar will be normal also. So and then the sample standard deviation would be s over square root n, right? So you would actually have a normal distribution, which is mu d, mean of the difference, and in x0 it's 0 usually. So the sample standard deviation would be how this, or d is x1 minus x2, how much these are in terms of the sample standard deviation, in terms of the standard deviation, and that's the tick mark, and we use t for d bar minus mu d. We actually look at d bar. because we'll look at how if I do a lot of the samples and compare and get a D bar, it is still distributed, and this is the standard error. Okay, this one, oh no, this is the standard error. So this is a new variable. You create a new data value, but a lot of software actually will create this difference variable as a new column. But if you want to do it instead this, you have to create them one by one. They help you analyze the data, but they don't create a new column for you. So a lot of time we would do it ourselves if we want to. So say, for example, let's say, let's do a new file. If you have two data from two different sample, right? So this is sample 1 and this is sample 2 and they matched. So for example, 10, 5, 6, 4, 2. And then this is 8, oops, 73, 67, 87, 56, like that. Okay, so let's say that this is two samples. We want to see the difference. Wow, the difference is really big, right? Maybe I'll just do so that they are not too big because the order of magnitude is actually quite significant. So we have these two samples and we want to know if actually it increased. So the difference actually that we are doing would be we actually do sample 1 minus sample 2. So this would be -8. So you would have some negative number. If the difference is 5 minus 2, 6 minus 7 is -1, 4 minus 8 is -4, and 5 minus 6 is -1. So you can see sample 2 most of the time increase. If you increase, the difference is negative because once you increase, sample 1 minus sample 2 is a negative number, right? So this is how we analyze it. So this is the step now. So to do the step, you actually run the hypothesis, like write a mean, write a claim, write a null hypothesis, write the alternative hypothesis, and then, so this is here. The main difference is you have to define the population, see which one is 1, which one is 2. That's very similar to proportion. You do that. But before you do anything, you have to determine if they are independent or dependent, even before you write down. Because if it is independent, you write population 1 and 2. If they're dependent, you should write the difference. You should write what subtract what is the difference. But in either case, if you have data, you enter them into stat_this. Now you set up the claim. The way the claim is set up is because this is about mean, right? So you would do mu1, mu2. And for dependent sample, you don't have mu1, mu2, you're processing D. You say mu D is something, greater or less than or something. If the second one is higher, then it is less than 0. If the second one is lower, then mu1 minus mu2 is positive. Okay. Then the third is the same. Now you're going to run the hypothesis. So I'm going to show you how to run it to get the test statistic p-value as well as the confidence interval. So the command to do it is, I have set this online, so is analysis, hypothesis testing, proportion to independent sample or not proportion, mean to independent samples or mean match pairs. So both of them are two samples. If they're not naturally paired, you use independent. If they are, then you do match pairs. Okay, so it is hypothesis test. Okay, so that's after that you get a p-value, you get a test statistics, which usually is t if sigma is not given, and then you have a C-level also at the end. But for dependent sample, you will do match pairs, right? You also will evaluate and everything. The rest is the same. If p-value is lower than alpha, you reject the null hypothesis and you will say there's sufficient evidence. And if the mean is If the claim is X0, then you say reject. If the claim is not, then you